Hello, today we're going to have a look at the third key area of the electricity unit at National 5 Physics, practical circuits. And the first we're going to look at are the idea of LEDs. Now, an LED is a diode, so it stands for light emitting diode in fact. And a diode will conduct, therefore an LED will light, if it's connected only in one direction. Now, generally an LED will conduct or emit light when it points towards the negative terminal of the circuit, like in this diagram here. So that LED would light. We would call that forward bias. If the LED is connected the opposite way round, it will not allow current to flow, and therefore it will not light, and therefore it's called reverse bias. Now, an LED requires a protective resistor, and that protective resistor has to be connected in series with the LED, and what it does is it restricts how much current can pass through the LED. Now, it's really common to be asked to calculate the size of protective resistor required. So here's an example of the sort of calculation you might have to do. If an LED requires 50 milliamps and a current of 0.7 volts across it, what size of protective resistor is required if it is connected to a 5 volt supply? So, here we can see the LED requires 50 milliamps of current passing through it and a voltage across it of only 0.7 volts. Now, there is a total of 5 volts going into this circuit. Therefore, the resistor has to take away the remainder of that voltage. So, if the voltage across the LED is 0.7, then the voltage across the resistor is going to have to be 5 minus 0.7, which is 4.3 volts. The current, because it's a series circuit, will be the same at all points. So the current passing through the LED is 50 milliamps, and the current passing through the resistor will be 50 milliamps. Therefore, to calculate the resistance of the resistor, we can use the voltage across the resistor and the current passing through the resistor with our Ohm's law formula. V equals I times R. So 4.3 volts equals 50 times 10 to the power of minus 3, because it's milliamps, times R. Or R equals 4.3 divided by 50 times 10 to the power of minus 3, which is a resistance of 86 ohms. So the size of the protective resistor required is 86 ohms. As I said, this is quite a common question, and it's also quite a common error that pupils make, because they forget to do that first subtraction sum. And you need to be using the voltage across the resistor in order to calculate the value of the resistor, not any of the other potentials given in the question. Speaking of potentials, potential dividers. Now, we met in the last video series circuits, and we talked about how in a series circuit the voltage, the supply voltage, is split between the components in the circuit. And I also mentioned in that if the resistance of the components in the circuit are of equal size, then the voltage would split equally. However, if the resistances are not of equal size, that won't happen. Now, a potential divider is a way of controlling how that potential splits. Now, it's quite simple. The voltage will split in a ratio that is equal to the ratio of the resistances. So here we've got R1 and R2, and the voltage across them, V1 and V2. So if R1 and R2 are equal, then V1 and V2 will be equal. If R1 is larger than R2, then V1 will be larger than V2, and so on. There's another formula that can be used. If we know the supply voltage, we can work out the voltage across one of the resistors. V2 equals R2 over R1 plus R2 times Vs. What this basically means is whatever fraction of the total resistance one resistor holds, that's going to be whatever fraction the voltage across that resistor will be of the total voltage. So here's a couple of examples. First one, calculate the value of V2 in the circuit below. So we've got two resistors and one voltage value, and we want to know the other one. So we can use this formula, V1 divided by V2 equals R1 divided by R2. And we can put our numbers into the formula. V1 is 12, R1 is the resistance that's giving us V1, which is 20, and R2 is 30. Now, my tip for working out these sort of calculations is that the value that you want to work out should always be on the top of the fraction. It makes life an awful lot easier. So in this case, the V2 is at the bottom of the fraction. So at this point, what I would do is flip both sides of this fraction the other way up. And I get V2 over 12 equals 30 over 20. And then it's a straightforward bit of maths to move the 12 to the other side, multiply the other side by 12. So 30 times 12 divided by 20. And that gives me V2 is 18 volts. And if you look at the circuit, you can see the 30 ohm resistor is 1.5 times as big as the 20 ohm resistor. And 18 volts is 1.5 times as big as 12 volts. So that ratio holds. Here's another example. This time, we're told the supply voltage is 6 volts. And we don't know either of the two voltages in the circuit, but we do know the two resistor values. So we're going to use this formula. V2 equals R2 over R1 plus R2 times Vs. So R2 is 3, R1 is 2, so 3 divided by 2 plus 1 times 6 gets us 3.6 volts. So that is my V2 value. Now, this is a potential divider. The supply voltage divides between the two resistors. Therefore, the voltage across the other resistor is going to be the supply voltage minus V2, which is 6 minus 3.6, in this case, which is 2.4 volts. And I've worked out the voltage across both. Now, some other types of resistors. We have the thermistor, which has that symbol, and it's a device where the temperature affects its resistance. It's a semiconductor device, in fact, and what happens is, as the temperature increases, the resistance decreases, or as the temperature decreases, the resistance increases. So we could draw a graph a little like that. We also have an LDR, or light-dependent resistor for short, and it works in a similar way, but as light level increases, as it gets brighter, the resistance decreases. As light level decreases, resistance increases. Now, the thermistor and LDR are ways of sensing changes in condition, so temperature changes or light changes. And they're often used in conjunction with a potential divider and a device called a transistor in order to control devices based on changes of condition. So we need a device that is an electronic switch. This is called a transistor switch. There are two types that we need to be aware of. First of all, the NPN transistor. It has the symbol like that. And they have what's called a switching voltage of 0.7 volts. What does that mean? Well, if we connect them in a circuit, there are three legs to our NPN transistor. The collector, which is at the top, the base, which sticks out the middle, and the emitter at the bottom. Now, it's controlled by the voltage between the base and the emitter, the potential difference between the base and the emitter. And the switching voltage tells us what voltage between the base and the emitter will turn that transistor on. So here we can see a device that causes that lamp to turn on when the voltage is above 0.7 volts and turn off when the voltage between the base and the emitter goes below 0.7 volts. The other type of transistor that we need to be aware of is called a Mosfet transistor. That's its symbol, and it has a switching voltage of around about 2 volts. Now, the parts of the transistor have different names, drain, gate and source, but it's a similar sort of way of working. Here, if the voltage between the gate and the source is greater than about 2 volts, the transistor will turn on and allow current to flow, lighting the lamp, and if it goes below that, then the lamp turns off again. Now, generally speaking, we'd see a circuit a bit like this. We can break this into 3 parts. On the left-hand side, we have a potential divider. Okay, this potential divider is comprising of a variable resistor and a thermistor. The base of our transistor, it's an NPN transistor in this case, is connected to the midpoint on that potential divider. So the base emitter voltage is the voltage across the thermistor. So we're always going to be interested in the voltage across the bottom component in the potential divider. Now, the other thing to notice here is we've got this thing called a relay switch up at the top. The relay is used as a way of separating a large voltage circuit from a small voltage circuit. So in this case, we've got the transistor and the sensitive electronics running on a small voltage of about 5 volts. But they're controlling a heater, which is running on a voltage of 230 volts. We don't want these two circuits to be connected together physically because 230 volts is too much for the sensitive electronics to function with. So we use this relay circuit. And basically what it is an electromagnet and a switch. So when current passes through the transistor, current will pass through the coil of the relay, causing it to become magnetic. That will drag the switch closed on the heater circuit, completing that circuit and turning the heater on, without there being any physical contact between the two circuits. Now, there are 4 different circuits that we need to be aware of. This one here is the first one. It's a light-controlled switch. And here, as the light level falls, the resistance of the LDR will increase. That's going to cause the voltage across the LDR to increase as well. Because remember, the ratio of the voltages in a potential divider are equal to the ratio of the resistances in a potential divider. And since our base emitter voltage is the voltage across the LDR in this circuit, if that voltage rises above the switching voltage, 0.7 in this case, because it's an NPN transistor, that's going to turn the transistor on, and that's going to allow a current to flow through the lamp, turning it on. So this is a circuit that comes on when it gets dark, perhaps automatic street lights. Another note, the variable resistor there can be used to set the exact level of light that you want the light to come on at. So you can alter the variable resistor to make it come on when it's darker or when it's slightly less dark. Here's another. Here, if you look at the circuit, the light-dependent resistor and the variable resistor have been swapped. So as the light level rises, the resistance of the LDR will decrease. And because the ratio of the resistances and the ratio of the voltages are the same, that's going to cause the voltage across the LDR to also decrease. But we're not interested in the voltage across the LDR. We if we are interested in what's going to happen to the transistor, it's the base emitter voltage that's important, which is the voltage across the variable resistor. Now, if the voltage across the LDR is decreasing, then that means, because it's a potential divider, the voltage across the variable resistor is going to have to increase. And when that voltage rises above 0.7 volts, that's going to turn the transistor on, and it's going to allow current to flow through the motor, turning it on. An example of this might be an automatic blind, which comes down when the sunlight gets too bright. Again, the precise light level that could turn the motor on or off can be set by altering the variable resistor. Here's a circuit that relies on temperature. So we've got a thermistor and a variable resistor in this circuit. So as the temperature rises, the resistance of the thermistor will decrease. Temperature goes up, resistance goes down. And because it's a potential divider and the resistance and the voltage ratios are equal, that's going to cause the voltage across the thermistor to also decrease. But because it's a potential divider, the total voltage between the two is still going to have to add up to the supply voltage, so the voltage across the variable resistor is going to increase. And when that voltage increases above the switching voltage, it's a Mosfet transistor here, so about 2 volts, that's going to turn the transistor on, and in this case, turn on the motor that drives the fan. So this might be a fan which comes on automatically when the temperature gets too high. Again, we could set the precise temperature that we want the fan to turn on at by varying the variable resistor. And the final circuit that we want to deal with is this one. And again, all that's different between this and the previous circuit is that the thermistor and the variable resistor have been swapped over. So as the temperature falls, the resistance of the thermistor will increase. That's going to cause the voltage across the thermistor to increase. And when that voltage between the gate and the source of the MOSFET increases above the switching voltage, again about 1.82 volts-ish, that's going to turn the transistor on, and in turn, that's going to turn the heater on. So this is a heater, which comes on automatically when it gets too cold. Again, we can set the exact temperature that we want the heater to turn on at by varying the variable resistor value. You'll have, quite likely, in your home somewhere, a thermostat where you can turn a little dial, which is effectively a variable resistor, to set the temperature that you want your heating to turn on at. And the inside working of that circuit is almost identical to this one. So that brings us to an end to the end of this video. I hope you found it helpful, and next time we're going to be having a look at power and electrical energy. Until then, bye for now.